Welcome back to Data Dynamics, where we dive into the captivating realm of data processing. I'm your host, Your Name, and today we're going to unpack a complex but essential topic in data engineering, stream processing. We'll explore the intricacies of stream processing, focusing on key aspects like fault tolerance, event ordering, and how we manage historical data. We'll also touch on derived data systems and their role in the world of streaming data. So, whether you're a seasoned data engineer or just curious about the field, stick around as we break down these concepts in a clear and engaging way. Let's start by discussing the core challenges of stream processing. Unlike traditional batch processing, which deals with fixed datasets, stream processing continuously handles real-time data. This ongoing nature introduces a variety of complexities, especially when it comes to fault tolerance and event ordering. Picture this. You're processing a stream of user activity logs. Each event comes with a timestamp, but what happens when those events arrive out of order? This creates a tricky situation. The uncertainty in event order can lead to non-deterministic joins, meaning that the same set of events could yield different results depending on how they're processed. This inconsistency can seriously compromise data integrity and reliability. To tackle these challenges, engineers utilize several techniques. One effective approach is assigning unique identifiers to changed records. By tagging each record with a unique ID, we can ensure that even if events arrive out of order, we can still accurately join them based on their identifiers instead of their arrival times. Another crucial strategy is checkpointing, where the state of the stream processing application is saved at regular intervals. If a failure occurs, the system can roll back to the last checkpoint, ensuring that no data is lost and that processing can continue smoothly. This method is vital for maintaining state across failures, allowing for what's known as exactly once semantics. Now, let's dive deeper into fault tolerance in stream processing. One of the main differences between batch and stream processing is how they handle faults. Batch processing can easily reprocess data from a fixed dataset, but stream processing requires innovative solutions for similar reliability. One solution is microbatching, where instead of processing each event individually, we group a small number of events together. This can help reduce the overhead of processing each event and make state management easier. However, it still requires careful handling to keep processing efficient and accurate. Another important concept is idempotence. In the context of streaming, idempotent operations ensure that even if an event is processed multiple times, the outcome remains the same. This consistency is crucial, especially when dealing with retries or failures. Let's shift our focus to managing state, particularly with windowed aggregations. When working with streams, we often want to aggregate data over specific time windows, like calculating the average number of logins per minute or total sales per hour. To achieve this, we need to maintain state for each window, which can be challenging, especially when events arrive late or out of order. One effective strategy is to use logs to rebuild state. By keeping a log of all events, we can reconstruct the state of our aggregations, even if some events are delayed or come in after the window has closed. Now that we've covered the foundational aspects of stream processing, let's pivot to derived data systems, focusing on materialized views. These systems provide quick access to processed data, but come with their own set of challenges. A key distinction here is between processing time and event timestamps. Processing time refers to when an event is processed by the system, while event timestamps indicate when the event actually occurred. This difference can complicate things, especially when dealing with straggler events, those late arrivals that come in after we think a time window is complete. For example, imagine you have a stream of activity events, like user clicks on a website. You might want to join these events with a database changelog to enrich the data, adding context to each click. However, if some click events arrive late, they might not match up with the changelog as expected, leading to incomplete or inaccurate data. In addition to self-joins within the same stream, we can also join changes from two different database changelogs. This allows us to create a continuous stream of updates to a materialized view, ensuring that our derived data stays up to date and accurate. However, managing these joins effectively requires careful attention to event timestamps and the potential for late arrivals. As we wrap up our discussion today, it's clear that stream processing is a complex yet rewarding field. The challenges of fault tolerance, event ordering, and historical data management require robust mechanisms and innovative solutions. From unique identifiers and checkpointing to microbatching and idempotence, there are numerous strategies we can employ to ensure reliable processing outcomes. And as we integrate derived data systems like materialized views, we must remain mindful of the nuances of event timestamps and the potential for straggler events. Thank you for joining me on this journey through the intricacies of stream processing. I hope you found this episode enlightening and that it sparked your curiosity about the world of data engineering. If you enjoyed today's discussion, be sure to subscribe and share this podcast with fellow data enthusiasts. Until next time, keep exploring the dynamic world of data.